Before a single shovel hits the dirt, we need to know exactly how a structure will handle the crushing weight of the earth above it. Today, we are going to build a digital twin of a utility tunnel and calculate its exact structural safety and stress distribution. We will be doing this using the GEO5 FEM program. FEM stands for Finite Element Method, which is a computational technique that breaks down complex structures into smaller, simpler pieces to calculate how they react to physical forces. And because GEO5 now uses cloud-based licensing, you can run these highly complex models directly from the job site or back at the office. Over the next few minutes, we'll start with a blank digital canvas, build the surrounding topology, generate a computational mesh, and run a full multi-stage model. For today's specific project, we are designing a standard utility tunnel. We will place this structure inside a layer of homogeneous soil, meaning the soil properties remain consistent throughout the entire excavated area. Mapping these interactions helps identify structural weaknesses during the design phase. Using this workflow allows you to refine your model before construction, providing data to support your safety and durability assessments. Step 1 is establishing the shape of the terrain. If you are working with a flat surface, simply input a single point in the interface. The program will automatically generate a flat terrain line across the workspace. Next, we draw the tunnel itself. Go to Settings and turn on the Snap to Grid function. This keeps your geometry precise. Use your mouse to draw 3 connected lines for the walls and floor, and then cap the top of the structure with an arc. At this point, engineers often encounter a critical calculation error. By default, the program's analysis boundary is too shallow. If the simulated ground beneath the tunnel isn't deep enough, the software cannot calculate accurate ground stress. This diagram shows exactly how we fix that. Open the Ranges interface and change the value of the deepest interface point to exactly 15 meters. Always verify this correction. Toggle back to the mesh generation frame and look at your workspace. You should clearly see that the specific area of analysis is now distinctly deeper. Now we generate the mesh. Click the Generate button, and the software will build an initial geometric mesh of triangles across the entire soil profile. This brings us to the second common point of failure. If you look at the default mesh immediately surrounding the tunnel structure, the triangles are too large and spread out. This coarse grid lacks the detail required for precise stress calculations. This side-by-side comparison shows the solution. On the left is our sparse default grid, and on the right our refined target. To achieve this, select each tunnel line in the refinements frame, input a specific radius and shorter length, and regenerate the mesh. Because the soil immediately touching the tunnel experiences the most volatile force, enforcing a dense, highly concentrated mesh right at the structure's edge captures those extreme pressure differentials and keeps flawed data out of your final design. Up to this point, everything we've done exists in a static topology mode, but real construction happens over time. We need to introduce chronological construction staging. In Stage 1, we calculate the initial undisturbed static stress of the earth. To do this, check your settings to ensure all soil areas are currently set to active. Once those baseline results are ready, we add a second construction stage. This specific stage is where we model the physical removal of the soil. This diagram illustrates the UI action required. Navigate to the activity frame, select the interior area of the tunnel, and set it to inactive. This mathematically simulates the physical excavation. The software's staging visualization tools immediately update. You can clearly see the empty void space where the earth was removed, leaving behind the newly exposed, unsupported edges of the surrounding soil. By isolating each chronological step of the excavation, we calculate exactly how the soil shifts and settles at each distinct phase. We identify the exact moment the ground becomes unstable, long before a physical crew starts digging. That newly excavated void will collapse if left alone. We need to immediately apply a concrete lining to hold back the earth. In the software, we represent this concrete lining by adding structural beams perfectly aligned with the perimeter of our excavated tunnel void. Apply the exact parameters for the lining. Choose a rectangular wall cross-section. Assign it a thickness of 0.2 meters. Open the defined catalog to select a C337 type concrete and apply these properties to all the free lines forming the tunnel shape. For this specific tutorial, we are using a basic elastic solution to calculate the forces. However, an elastic solution assumes materials bounce back perfectly after being compressed, which is not enough for real-world structural analysis. This graph compares our basic elastic model, the straight linear trajectory, against a curving complex deformation line. That curve represents the Moore-Coulomb model. Moore-Coulomb is a mathematical framework that specifically calculates how soil and rock permanently shear and fail under compressive stress. To accurately mimic ground deformation, you must use advanced FEM models like this, or the hardening soil model. With the lining parameter set, hit the Generate button one last time. The software's enhanced solver speed processes these complex calculations rapidly, outputting our final data. If you want to generate trustworthy predictive data, you cannot cut corners. Pairing exact structural materials with advanced realistic soil models is the only reliable way to know your design will hold up in the field. Now we interpret the final results. On the main screen, observe the color-coded stress changes strictly in the Z direction, and look closely at the calculated physical deformation of the overall structure. You can isolate specific metrics. For example, select the Bending Moments tool to display a focus distribution map showing where the structural walls experience the most twisting force. Open the Visualization Settings frame. Click the Save button and assign a unique name to this specific view so you can retrieve it instantly later. When you are building a reporting package or presenting directly to a client, you can rapidly toggle between these saved views, giving you instant access to your exact stress and bending moment data without waiting for the model to recalculate. This visual evidence validates the structural behavior of your design. It provides the data necessary to transition from simulation to physical construction. For more on advanced material models, check out the other tutorials or reach out to our support team.